In 1969 AB3, we're given the function f of x is equal to 1 over x plus ln of x, defined only on the closed interval from 1 over e to e. We want to showing our reasoning, determine the value of x at which f has its absolute maximum and absolute minimum. What we need to do for this, since this is a continuous function on a closed interval, we want to find the critical values and also test the endpoints. So let's start with the derivative. We have f of x is 1 over x, so that's x to the negative 1 is going to give us negative 1 over x squared. And the derivative of ln of x is going to give us 1 over x. Now if we wrote these with negative exponents, we'd get negative x to the negative second plus x to the negative first. Factoring out the greatest common factor, which we can make x to the negative second, or even negative x to the negative second. Then that'll leave us 1, and then we'll need a minus. Negative times negative would bring us back to positive, and multiplying two numbers with the same base, we add our exponents. We need to add exponents to get to negative 1, and so negative 2 plus 1, so that would just be x. Now we are on the interval from 1 over e to e, so we don't need to worry about the vertical asymptote at x equals 0. And so the only place where we'll have a 0 for that is at x equals 1. So to find the absolute max and min, we just need to test the original function at the endpoints and critical values. So we'll test f of 1 over e, f of 1, and f of e. Obviously we're going to plug these numbers back into the original function. So we have 1 over e, which is e. Ln of 1 over e is ln of 1 minus ln of e, so that's 0 minus 1. F of 1 is going to be 1 plus 0, or just 1, and f of e is going to be 1 over e plus 1. Now, not having a calculator here, you have to do a little bit of analysis. E is roughly 2.718, so e minus 1 is going to be about 1.718, and that's still greater than 1. And if e is 2.718, 1 over e is roughly 1/3, so that one would be about 1.3. And from that simple analysis, we can tell that the maximum is at x equals 1 over e. The absolute minimum is at x equals 1. For what values of x is the curve concave up? For this, we'll need the second derivative. So we'll go back to the unfactored form of the derivative, negative x to the negative second. We'll bring down the negative 2, so it'll be positive 2x to the negative third. Then bring down the negative 1, so it's minus 1x to the negative second. If we need to factor, we'll bring out x to the negative third, and that leaves 2 minus x. So our only 0 in that case will be at x equal 2, which is in the interval from 1 over e to e, as was the 0 for the first derivative, x equals 1. We set up a sign chart and find some test values in there. We're testing the second derivative at 1. The first term is going to always be positive when x is positive. So 2 minus 1 is positive. 2 minus 2.5 is negative. So the curve will be concave up from x equals 1 over e to 2. So I plot the points that I have there for 1 over e, for 1, and for e. Then I just need to make sure that I have a relative minimum at x equals 1, that I'm concave up between 1 over e and 2, and that I have a point of inflection at 2 and concave down from 2 to e. So I draw the line segment in from 2 to e, concave down. I draw in the concave up segment from 1 over e to 2, and it's a very slight grade in there. And if you're concerned about your lines not coming out exactly right, you can make those up and down arrows to indicate that you want it to mean concave up, concave down. You see, I'll also put a dashed line for where the point of inflection is. And part D we won't cover in this video.